Hello everyone. Today we look at Chapter 2, and Chapter 2 will walk us through looking at organizing and summarizing data. This can be a very useful chapter for you because we kind of expand on this through the course, but this is also something you may be able to use for your project to kind of simplify your data analysis, which we'll talk about that throughout this 8 weeks. Section 2.1 looks at organizing qualitative data. When we collect data from a survey or some kind of designed experiment, we get raw data. That raw data can then be organized into something like a table, a graph, or some type of numerical summary like we'll look at in Chapter 3, our next chapter. This chapter looks pretty heavily at frequency distributions, and this is a very common thing for statistics books to cover right off the bat. A frequency distribution lists categories of data and the number of occurrences that data happens. So what we'll be doing in this chapter is looking through several examples that are extended out. Some of these deviate from the chapter to give you a little bit of a different look at things. So let's take an example. So we all remember that I like using collars of different candies to do statistical studies. It's just kind of an interesting topic area that students usually enjoy working with. So the data on the next slide that we're going to be looking at represent the collar of M&Ms in a bag of plain M&Ms, and we're going to construct a frequency distribution. So this slide shows the breakdown of all of the M&Ms. It just designates what color they are. This is all of our data. We categorize that in our frequency table. So what you see here is a frequency table. We list out by color, tally marks for the number of occurrences, and then we count those, and that's our frequency. So our frequency really is, our tally marks really are our frequency. The frequency just totals it into a numerical amount. The relative frequency is the proportion or percent of observations within a category using the formula the frequency you have divided by the sum of all of those frequencies. A relative frequency distribution lists each category of data with the relative frequency. So now we're going to use that frequency distribution that we just saw a little bit ago with our M&M distribution for the plain M&Ms. And we go back to this. This was the frequency table that we'd used. For each one of these things, we're going to take the frequency and divide by the total. So we're missing one line here because if I go back, green had 5 tally marks. It's just cut off of this slide. So if we added all of the frequencies in the second column over from the left, the frequency column, it comes up to 45 when I count that 5 green that's missing from the other slide. So I take every number, divide by 45, that gives my relative frequency. This puts things into perspective for me. I can do more comparisons if I wanted to look at different types of M&Ms, different bags of M&Ms, different types of candies to compare to. That relative frequency puts it on a comparable ground for me. So the next thing we look at is constructing bar graphs. So a bar graph lets you look either horizontally or vertically at your data that you've calculated in your frequency and relative frequency calculations. We draw rectangles of equal width for each category. The height represents the category's frequency or relative frequency. We're going to use our M&M data again and construct a frequency bar graph and a relative frequency bar graph. We go back to our data that we've been using. We plot it out. First by frequency here, so we can see our color distributions, and I can look at this and see there's many more occurrences of brown than there are of any others. Blue is the lowest color being represented in the bag. I go back to my relative frequency table and I get those amounts and I plot those out on a bar graph. And again, you can see my relative frequency, brown higher, yellow coming in second, red third, orange is closely fourth, and then you can go over and see that green fifth, and blue is coming in dead last to sixth. A Pareto chart is a bar graph where the bars are drawn in decreasing order of frequency and relative frequency. So what I just talked about is laid out here in this Pareto chart for our relative frequency. So it shows the distribution. So you can see from left to right the most occurrences of colors to the least here. So that's a good visual to use this kind of chart. Oh, sorry. Side-by-side bar graphs can be useful too. Suppose we want to know whether more people are finishing college today than in 1990. We could draw a side-by-side bar graph to compare the data for the two different years. The data sets should be compared using relative frequencies because different samples or proportions can be put in the same perspective when we convert them to percentages. So here's our data. This represents the marital status in millions of U.S. residents 18 years of age or older in 1990 and 2006. It wants us to draw a side-by-side relative frequency bar graph of the data. So we see our marital status and then 1990 and 2006 numbers. Now we can take that data, plot them in side-by-side bar graphs. So you can see that there. Horizontal bars can also be used. These are preferable when the category names are lengthy. So here we go back to educational attainment. So in 1990 versus 2013, we have not a high school graduate, high school diploma, some college no degree. You can notice these titles are a little bit lengthier. So this view might be better. A pie chart is a circle divided into sectors. Each sector represents a category of data. The area of each sector is proportional to the frequency of the category. So in a sample pie chart, we go back to our marital status data. Looking at residents 18 or older in 2006, and we have our frequencies, and we're going to draw a pie chart. So the pie chart just takes those categories, it labels it over to the right in the legend, and it lists them out and shows what chunk of that circular region or that pie is taken up by that listing. So we can see here over 58% of the pie chart married, 25% never married, and so on. Section 2.2 looks at organizing quantitative data. So we look at the popular displays for that. Quantitative data needs to first be determined if it's discrete or continuous. If the data are discrete, and there are relatively few different values of the variable, the categories of data or classes will be observations, as in qualitative data. If the data are discrete, but there are many different values of the variables, or if the data are continuous, the data, or the classes, must be created using intervals of numbers. The following data represent the number of available cars in a household based on a random sample of 50 households. So we need to construct a frequency and relative frequency distribution. So you'll notice a lot of numbers as low as 0, and just by quick glance as high as 5. So we listed out here number of cars, the tally marks, the total of the tally marks, which is our frequency. Totaling our frequencies to get to 50, we add each frequency by 50 to get our relative frequency, just like we did before. A histogram is constructed by drawing rectangles for each class of data. The height of each rectangle is the frequency or relative frequency of that class, and the width is the same as the rectangles touching each other. Very similar to the bar graphs we just looked at in the last section. We go back to our data here with number of cars, and we list out our frequencies. So this lists out based on our previous data. So for number of cars, we have 0, frequency of 4, relative frequency of 0.08. So here you see this just has our frequency numbers plotted out. So I can look at this and say that the average household has 2 cars. Now if I look at the relative frequency, that puts it into perspective on that percent value, and still 2 is the prevailing number, but this gives a more proportional look, so I could compare different size groupings or samples within populations. Classes are categories in which data are grouped. When a data set consists of a large number of different discrete data values, or when a data set consists of continuous data, we have to create classes by using intervals of numbers. The following data represents the number of persons aged 25 to 64 who are currently work disabled. So it gives the age and the listing for the number in thousands. The lower class limit of a class is the smallest value, while the upper is the largest value within that class. The lower class limit of the first is 25, of the second it's 35. The upper class limit of the first class is 34, of the second is 44. The class width is the difference between consecutive lower class limits. So if we look at between the first and second groupings, we take 35 for the second grouping lower limit minus 25 for the first age limit range to get 10. The following data represent the time between eruptions in seconds for a random sample of 45 eruptions at the Old Faithful Geyser in Wyoming. Construct a frequency and relative frequency distribution of the data. So our numbers are here. The smallest data value is 672. The largest is 738. We're going to create the classes, so the lower class limit of the first class is 670, and the class width is 10, and obtain the following classes. So you can see them listed out. We're going to plot that out in our table to get our frequency and relative frequency like we've been doing, and we have that data. So you may be asking yourself how you get those class limits. The choices for the class limits are somewhat arbitrary. Depending on your data, you may need wider or narrower class limits. There's not one exact correct limit or value to use. But you can kind of tell by looking at your data. Pull the lowest value and the highest value, and take the difference and estimate out how many classes you think you'd want. So there's not one correct frequency distribution for a particular set of data. Some better illustrate patterns with the data than others. So constructing the frequency distribution can be an art form, especially with determining those class levels. You need to use the distribution that seems to provide the best overall summary of your data. Here we look at the time between eruptions in seconds, where we have classes showing a distribution with a 5. So notice between the first and second, from 670 to 675. So we list out, put our tally marks in, we get our relative frequencies. I can look over to the side, and the right side, and see my relative frequency. And that's one way to look at the data. The first thing that we need to do is choose our lower class limit of the first class. We do that by choosing the smallest observation in the data, or a convenient number slightly below. And I usually like to round it down to an even ending in 0 or 5 type number. Then we need to decide on the number of classes, and again, this is an arbitrary number. It is something that you may need to kind of test out and experiment with a few different levels. Typically, there should be between 5 and 20 classes. That's fairly standard. The smaller the data set, the fewer classes you want to have. If I take my largest data value minus my smallest data value in my set and divide by the number of classes I want to have, that'll give me my class width. We need to round that up then to a convenient number. So here we look at time between eruptions and we have frequencies. So this is the frequency showing our values between 670 and 680, 680, 690, and so on. So that lists that out. Now let's assume that we use a class width of 5 instead of 10. And notice what my data does. It's more varied. I can see trends and patterns in that more easily. So stem and leaf plot is next. You've probably will vaguely remember this from even elementary school classes. This is where we use digits to the left of the rightmost digit to form the stem. Each rightmost digit forms a leaf. For example, a data value of 147 would have 14 as the stem and 7 as the leaf. In an example, an individual is considered to be unemployed if they do not have a job, but are actively seeking employment. The following data represent the unemployment rate at each of 50 United States plus the District of Columbia in June 2008. So we see our data listed out here. Quite a bit of data. This is listing out all of our states. We let the stem represent the integer portion of the number, and the leaf will be the decimal portion. For example, the stem of Alabama, which was 4.7, will be 4, and the leaf will be 7. We list out our data. So all of these numbers, 2.8, 3.8, 3.8, 3.8, 3.3, and so on. So then we look at that data again, but putting the numbers in order from smallest to greatest on the right side, on the leaf side, just to be able to view that more easily. This slide just shows the step-by-steps from what we just did. When our data appear rather bunched, we can use split stems. So the stem and leaf plot shown on the next slide reveals the distribution of the data better. Just like determining class intervals in frequency histograms, judgment plays a major role here with our stem and leaf plot. There's no such thing as an absolute correct stem and leaf plot, but some are better than others. So here you can see we split out our stem and leaf plot, and we categorized our variables in the, so say for example, 3.0 to 3.4 range, 3.5 to 3.9, and then we did that with each stem number going down. This spreads our data a little bit better and gives you a better view of the spread of it. Once a frequency distribution or histogram of continuous data is created, the raw data is lost, unless we report that with a frequency distribution. However, the raw data can be retrieved from the stem and leaf plot. A dot plot is drawn by placing each observation horizontally in increasing order and placing a dot above the observation time. Say we go to this data, back to the number of available cars and a sample of 50 households. So we want to draw a dot plot of that data. And basically, we're going to go across the bottom axis and list 0 through 5 cars, because that was our results that we used. Each time that we have one of our values falling in that range, we put a dot above that value. So here we can see also that 2 is the prevailing number of cars per household in that sample of 50. In section 2.2.7, we're looking at identifying the shape of a distribution, and this is something we'll look at over the course of the next several chapters. A uniform distribution is where the frequency of each value is evenly spread across the values of the variable. A bell-shaped distribution, the highest frequency occurs in the middle, and then both sides trail off into fairly equal tails to the right and left of the middle. Skewed right means the tail to the right of the peak is longer than the tail to the left, and skewed left is the opposite of that. If you'd like to see that visually, this shows a uniform pattern in the upper left, bell-shaped in the upper right, and then the skewed right and left in the lower left and right. That was confusing, but those values respectively. A bell-shaped or symmetric curve is one that we look at quite a bit in statistics. When our data falls like this, we can make a lot of assumptions about confidence levels with this type of distribution. So we're going to look at an example. It says, identify the shape of the following histogram which represents the time between eruptions at Old Faithful. So we see that here. If we go back to look at our distributions, we see that it looks slightly more skewed left than any of these other distributions. If the value of a variable is measured at different points in time, the data are referred to as time series data. A time series plots the time in which a variable is measured on a horizontal axis and the corresponding value on the vertical axis. Line segments are then drawn connecting the points. The data to the right shows the closing prices of the Dow Jones Industrial Average for the years 1990 through 2007. If we take that data and we plot it with our years at the bottom in the horizontal axis and our closing values in the left side vertical axis, we plot our points and connect the lines to see those closing values. This is a very normal viewing of the Dow Jones Industrial Average that you can even look at it on a daily basis, spread out by hour. Section 2.3 looks at graphical misrepresentations of data. In a quote from the chapter, the only science that enables different experts using the same figures to draw different conclusions. That's statistics. The data in the table represent the historical life expectancies in years of residence of the United States. Construct a misleading time series graph in A to show that life expectancies have risen sharply, and in B, construct a time series graph that is not misleading. So we have our values here. In A, with a misleading amount, in our graph, we have our years at the bottom horizontal axis from 1950 to 2000. Our life expectancy starting out at 68 to 78. That shows a pretty sharp increase. In B, the same graph, but our vertical axis, our life expectancy in years, we're going to start that out at 0 and plot it up to 80. And you'll notice that gives a much more even line there. We don't just start out life expectancy at 68 because people are born and die at different levels, so we need to factor in from birth to death in B. The National Survey of Student Engagement is a survey that, among other things, asks first-year students at liberal arts colleges how much time they spend preparing for class each week. The result of the survey from 2007 are summarized on the next slide. So we want to construct a pie chart that exaggerates the percentage of students who spend between 6 and 10 hours prepping for class, and then a pie chart that's not misleading. There's our data. We plug that into a pie chart. We turn that pie chart on its side, make it a 3D view, and spin it around to the hours of 6 through 10. That makes that look so much larger than it actually is. If we plot that and show a top view of it, it evenly shows the spread from 0 hours up to 31 to 35 hours. So just some guidelines for constructing good graphics. Title and label the graphic axes clearly. Provide explanations when you need to. Include units of measurement and a data source when appropriate. Avoid distortion. Never lie about the data. Minimize the amount of white space in the graph. So use the available space to let the data stand out. If scales are truncated, be sure to clearly indicate that for the reader. Avoid clutter, such as excessive grid lines and unnecessary backgrounds or pictures. Don't distract the reader with that. Avoid 3 dimensions, as we saw in that pie chart. They may look nice, but they distract the reader and often lead to really focusing in on one thing in it, misrepresenting the rest of the graph. Do not use more than one design in the same graphic. Sometimes graphs use a different design in one portion of the graph to draw attention to that area. Don't try to force the reader to any specific part of the graph. Let the data speak for itself. Avoid relative graphs that are devoid of data or scales. So those are just some tips for constructing clean graphics and graphics that aren't going to incorrectly influence your reader's perceptions. So that wraps up Chapter 2. We looked at a lot of different examples to reinforce the chapter. If you ever have any questions on that, feel free to let me know.